Welcome to this lecture 3 of Fundamentals of Transport Processes. We get down to the hard work now. We start with vectors and tensors. A brief introduction. In this particular lecture, we will or in this particular course, we will be dealing only with what are called orthogonal coordinate systems. That means coordinate systems in which the three axes are perpendicular to each other. So, in three-dimensional space, you can have only three perpendicular axes. My first part of the discussion will be on the Cartesian coordinate system. And then later on we will go back and look at how to deal with spherical and cylindrical coordinate systems. A lot of what we do for Cartesian coordinate systems will carry through to spherical and cylindrical coordinate systems, with the only modification that the operators, the integral and differential operators, will have slightly different forms. So, Cartesian coordinate system, where I will use three orthogonal axes x1, x2, x3. Okay. Rather than using x, y and z, we will use the axis x1, x2 and x3. It will become a little clearer a little later why we are choosing to do it this way. The unit vectors in this coordinate system are E1, E2 and E3. These are the three unit vectors perpendicular to each other. We will use E1, E2, E3 instead of I, j, k or Ex, Ey, Ez. So, any vector can be written in terms of its components. If I had the velocity, for example, the velocity vector representing the fluid velocity at one particular location, I can write this as u vector is equal to u1 e1 plus u2 e2 plus u3 e3. Okay, so, that is the velocity vector. It consists of the components plus the unit vectors, and the three components. So, any vector can be written in this form. For example, if I had some other vector, say I call it a vector, this is a1 e1 plus a2 e2 plus a3 e3. Okay. Some other vector b is b1 e1 plus b2 e2 plus b3 e3. Okay. I can take the dot product of these two. The dot product of two vectors is a scalar. Okay. It is equal to a dot p. You can write it in various ways. So, if I had two vectors, a vector and b vector, it is written in various ways. One is in terms of the angle between these two. Okay. It is written as the modulus of a, the modulus of b times cos of the angle between them. For the present course, we will write this just in terms of the components, a1 b1 plus a2 b2 plus a3 b3. Okay. Now, rather than write these vectors out in long notation, I can just write it simply in a simplified form. I write this as summation I is equal to 1 to 3 of ui times ei vector. Okay. So, if I is equal to 1, it is u1 times e1 vector, I is equal to 2, it is u2 times e2 vector, and I is equal to 3, it is u3 times e3 vector. So, that gives us the long form that we had above. Similarly, for these vectors, I can write them as summation I is equal to 1 to 3 of ai ei vector So, this has two parts, one is of course the unit vector and the other is the component. A I and B I are the components, E I's are the unit vectors. The dot product of course is a scalar. Okay. So, this is just equal to summation I is equal to 1 to 3 of A I times B I. Okay. In the last lecture we had also looked at tensors. Okay. One tensor that we had looked at, for example, was the stress tensor. Okay, so let us look at that. The stress tensor, okay, is defined as I will use T here instead of tau, not to be confused with temperature. I will use capital T, okay, for the stress tensor, T x y. Okay. So, the simplest case you can consider is, for example, the flow between two flat plates, where the flow direction is x, the normal direction is y. Okay. Then I have some kind of a linear velocity profile. The shear stress acting on the surface is given in Newton's law of viscosity by mu dux by dy if there is a linear velocity profile, okay, and if there is only one directional flow. We will see a little later that this is not the most general form. This is only when you have one directional flow for a linear velocity profile. Okay. What is the definition of the stress? This is equal to force per unit area in x direction at a surface with unit normal. Okay. Note that this is outward, unit normal in y direction. So, there are two directions here. One is the direction of the force is in the x direction, the outward unit normal of the surface. The surface, any surface within this three-dimensional system can be completely defined by the line perpendicular to that surface, the vector perpendicular to that surface. Okay. So, a surface in three-dimensional space is completely defined by the vector perpendicular to the surface. It is preferable to use unit vector just to make sure that there is no ambiguity. So, with an outward unit normal, okay, unit vector normal to the surface in the y direction. So, for example, the force exerted on this bottom plate here, for this bottom surface, the outward unit normal to this bottom surface, that is the unit normal that faces into the fluid. Okay. For this bottom surface, the outward unit normal is upward. For the fluid volume itself, the outward unit normal is downwards. Okay. So, the force exerted by the fluid on the surface is opposite to the force exerted by the surface on the fluid. So, the force in the x direction, that is the force in this x direction acting at a surface whose outward unit normal is in the y direction, the force per unit area, that is the stress tensor. So, there are two unit vectors here, or two directions associated with this quantity called the stress. One is the direction of the force that is exerted on the surface. The force of course depends upon the orientation of the surface, and so there is a surface orientation which is the second direction. Okay. So, there are two directions here. Okay. So, this is the stress, one particular component of the stress. Okay. But if I am sitting at some particular location, okay, if I am sitting at some particular location in the fluid, the stress is defined at that particular location. Okay. So, I can construct a small box around that location. Okay. And if I expand out this box, okay, if I expand out this box, this differential volume, this differential volume, this fluid element sitting inside the fluid has forces exerted on it in all directions. Okay. So, the force on the top surface Okay. The top surface has a unit normal in the plus x3 direction. The top surface has a unit normal in the plus x3 direction. The bottom surface has a unit normal in the minus x3 direction. So, at this top surface there is some force, okay, some force. That force of course decreases as the area decreases, because the force is proportional to the area in the limit as the area goes to 0. The component of this force in the x1 direction, okay, this force will have 3 components once again. The component of this force in the x1 direction is T13. Force direction is x1, unit normal direction is x3. So, T13. The component in the x2 direction is T23 and so on. Okay. So, the first index is associated with the force, the second index is associated with the direction of the unit normal. Okay. So, for any general, okay, for any general component can be represented as Tij is equal to force per area in the I direction. Okay. Let me write that as xi direction to avoid confusion. Xi direction acting at a surface with outward unit normal in xj direction. Okay. The force per unit area in the xi direction acting at a surface with outward unit normal in the xj direction. So, that is the definition of the stress. Okay. So, rather than so there are now total of 9 components. I can go from 1 to 3. So, the force can have 3 different directions. At that particular location, the unit normal to the surface can also have one of 3 directions. Okay. So, you have 3 directions for the unit normal, therefore, total 9 directions for the total stress, similar to 3 directions for the velocity, 3 components of the velocity. In this particular case, since there are 2 fundamental directions associated with the stress, there are now 9 components of the stress. I can write this in short form. Okay. Okay, just as I had written, for the velocity vector, u vector is equal to u1 e1 plus u2 e2 plus u3 e3. Okay. Similarly, I can write the stress. It now has 2 fundamental directions associated with it. Each direction has 3 components: direction of force, direction of unit normal. So, I can write the stress as T11 E1 E1 plus T12 E1 E2 plus T13 E1 E3 plus T21 E2 E1 plus T22 . Then I have these other plus T . Okay, so, it has total of 9 components. Just as I had written this as summation I is equal to 1 to 3 of ui ei, I can write this as summation I is equal to 1 to 3 summation j is equal to 1 to 3 of T I j E I E j. Okay. So, what do each of these mean when I have my differential volume? Okay. I have 3 directions for the unit normal. Okay. So, the first is this is in the x3 direction, this is in the x2 direction. So, this unit normal is E2. And coming out of the board for you is the unit normal E1. So, the front and back surfaces of this volume have unit normals in the plus E1 and minus E1 direction respectively. The right and left have unit normals in the plus E2 and minus E2 directions. Top and bottom have unit normals in the plus E3 and minus E3 directions. At each of these surfaces there is a force acting, okay, due to either fluid pressure or due to fluid flow, and the component of the force acting on this front surface in the one direction is T11 per unit area, in the two direction is T21, force direction is 2, unit normal direction is 1, etc. Okay. So, this just as this velocity vector contains all the information about the velocity at a given location. Okay. This vector contains all the information about the velocity at a given position in space. It has 3 components, and you can also get the vector direction out of these 3 components. Similarly, this object, this stress tensor, which has 9 components in it, contains all the information about the force per unit area at a given location, okay, for the force direction as well as the direction of orientation of the surface. Okay, it contains all of that information in these 9 components, okay, and I can write it out this way. Okay. We will see a little later in some applications it is also convenient to write this in a matrix form. Okay, the stress tensor is sometimes conveniently written in a matrix form. There are certain advantages to writing it in this form. We will see that as we go along in this course. Okay. So, this is the notation for the stress tensor. Okay. And of course, you can have tensors with more fundamental directions. Velocity has one fundamental direction, it is a first order tensor. Temperature field has 0 directions, it is a scalar. So, it is a 0th order tensor. The stress has 2 directions, it is a second order tensor. You could in general have tensors with 3 fundamental directions, third order, fourth order, fifth order, and so on. The first order tensor, which is a vector, has 3 components, 3 power 1. The second order tensor has 2 fundamental directions. Each of those directions has 3 components. So, you get a total of 9, 3 power 2. The second order will have 3 power 3, I am sorry, the third order will have 3 power 3, fourth order will have 3 power 4, and so on. We will not go much further than second order in this particular course, but it is important to realize that this stress tensor as defined is a second order tensor, which has information about all components of the force per unit area at a given location. As I had briefly introduced in the previous lecture, the force per unit area is essentially the momentum flux. Okay. So, the flux direction, there are 3 flux directions, there are 3 force directions. Therefore, you have a total of 9 components. Okay. Now, we had introduced the dot product in the previous slide. Okay. The dot product of 2 vectors, you just is a scalar. Okay. So, you take the dot product of the 2 the components, you multiply the components with each other and add it up. In terms of the unit vector, okay, I can rewrite the dot product as follows. Okay. A dot B is equal to I is equal to 1 to 3, dotted with the second vector. Okay. So, you are dotting 2 vectors. Note here that I have used 2 different indices for the 2 vectors. In the first case I have used I, second case I have used j. The reason will become clearer in a little bit. Okay. So, when you take the dot product of 2 components and unit vectors, you multiply the components, dot the unit vectors. Okay. 1 to 3 okay, of multiply the components and dot the unit vectors. Multiply the components, dot the unit vectors. Now, what is E I dotted with E j? Okay. I is 1, 2 or 3, j is also 1, 2 or 3. Okay. So, if I and j are equal, then E I dot E j is equal to 1, because the two are both unit vectors. If I and j are not equal, then E I dot E j is equal to 0, because the vectors are orthogonal. So, E 1 dot E 1 is equal to 0, I am sorry, E 1 dot E 1 is 1, E 1 dot E 2 is 0, E 1 dot E 3 is 0, and so on. Okay. So, this dot product E I dot E j is also written as this is equal to 1 if I is equal to j, and is equal to 0 if I is not equal to j. Okay. So, it is either 1 or 0. If I is equal to j, it is equal to 1. If I is not equal to j, it is equal to 0. Okay. It is written by the simple delta I j. Okay. Delta I j often called as the Kronecker delta function. Okay. Delta I j is 1 if I is equal to j, delta I j is 0 if I is not equal to j. Okay. So, therefore, I can write A dot B as summation I is equal to 1 to 3, summation j is equal to 1 to 3 of A I B j delta I j, because E I dot E j was equal to delta I j, which was 1 if I is equal to j, and it was 0 if I is not equal to j. Now, I have summation I is equal to 1 to 3 of A I B j times delta I j. I have two summations I is equal to 1 to 3 and j is equal to 1 to 3. Of course, delta I j is non-zero only if I is equal to j. So, when I take the summation over j is equal to 1 to 3, I will get a non-zero result only when I is equal to j. Therefore, I can rewrite this as summation I is equal to 1 to 3 of A I times B I. Okay. Because in the second summation, only when j is equal to I do you get a non-zero result. Okay. In the second summation, only when j is equal to I do you get a non-zero result. Therefore, I can replace j by I and remove that summation, okay, and I get summation of A I B I. Okay. This, as you will recall, is exactly what we had when we discussed the dot product earlier. Okay. This is exactly what we had when we discussed the dot product. Okay. One important point to remember here is that the indices that I use for these two have to be different. Okay. Because one index is getting summed over from 1 to 3, the other is also getting summed over from 1 to 3. It is not the same as both of them simultaneously getting summed over from 1 to 3. Okay. So, that is the dot product. Okay. The other vector product that you are used to is what is called the cross product. Okay. A vector cross B vector. Okay. There are many ways to write it. One is to write it as A magnitude of A magnitude of B sin theta. Okay. The other way that it is usually written is to take the determinant of the matrix which consists of E 1, E 2, E 3, A 1, A 2, A 3, B 1. Okay. You take the determinant of that matrix and you will get a vector. Okay. You will get a vector which is E 1 into A 2 B 3 minus A 3 B 2 plus okay. So, that is the cross product written out in long form. Okay. It is a vector which is perpendicular to both vectors A vector and B vector, okay, and it is equal to 0 if both vectors are collinear. For our purposes, rather than write it this way, we will write the cross product in terms of a dot product, okay, using what is called the anti-symmetric tensor. Okay. So, for example, if I have the cross product A cross B, okay, what I am going to write this is as summation I is equal to 1 to 3 okay, E I epsilon I j k A j B k. Note this is now a vector. This is a vector because it has one unit vector. Okay. Whenever there is a vector, there is a free index and there is a unit vector, and when you have a dot product, the index is repeated. As you can see, when you have a dot product here, you have the same index repeated 2 times. Okay. So, if I write it this way, what is this epsilon? Okay. Epsilon is what is called the anti-symmetric tensor. Okay. Is equal to 1 if I j k is equal to 1 2 3 3 1 2 is equal to minus 1 if is equal to 0 if any 2, well, let us just say it is equal to 0 otherwise. It is equal to 0 otherwise. Okay. So, epsilon I j k, if I j and k are 1 2 3, 3 1 2 or 2 3 1, then epsilon I j k is 1. If I j k are 1 3 2, 3 2 1 or 2 1 3, then it is equal to minus 1, and 0 otherwise. Otherwise means that any 2 of these indices I, j and k are repeated, okay, because there is only 6 combinations in which all 3 are not repeated. In all other combinations, there have to be at least 2 indices that are repeated, and if 2 indices are repeated, then this is identically equal to 0. Okay. Notice one thing about this tensor. If I interchange any 2 indices, I get the negative of its value, okay. That is epsilon I j k is equal to minus epsilon I k j. That is why it is called an anti-symmetric tensor, okay. That is epsilon I k j and epsilon I j k are, you go from one to the other by multiplying by minus 1. So, in this case I have interchanged 3 and 2 and I get minus 1. In this case, I have interchanged 1 and 2 and I get minus 1, and vice versa. Okay. So, that is why it is called the anti-symmetric tensor. Okay. How is this useful for cross products? Okay. I have here my formula for the anti-symmetric tensor, okay, for use with cross products. Okay. So, let us just put this in and use this formula, okay, keeping in mind that epsilon I j k is non-zero only when all 3 indices are different. Okay. It is non-zero only when all 3 indices are different, and it is 0 if any 2 of these indices are the same. Okay. So, let us just implement this formula. The first is when I is equal to 1. Okay. In that case, the unit vector E I is just E 1. Unit vector E I is just E 1. Once I is equal to 1, then j and k have to be either 2 and 3 or 3 and 2, okay, because they cannot repeat. Okay. So, if j and k are 2 and 3, then I have epsilon I j k is 1. If I j k is 1 2 3, if I j k is 1 2 3, then epsilon I j k is 1. So, therefore, I have plus 1 into A 2 into B 3. Okay. Okay. So, that is when epsilon I j k, j and k are 2 and 3, I is 1. There is one other combination which is non-zero, that is when j and k are 3 and 2. Okay. and when j and k are 3 and 2, epsilon I j k, as you can see from here, is minus 1, okay, when j and k are 3 and 2. Okay. In that case, I get minus 1 into A 3 into B 2. Okay. So, these are the only results left over when I is equal to 1, because all other cases epsilon I j k is equal to 0. Okay. Then I have for I is equal to 2, in which case the unit vector has E 2. Okay. I is equal to 2, that means j and k have to be either 3 and 1 or 1 and 3. Okay. If j and k are 3 and 1, then I get plus 1. If j and k are 3 and 1, I is 2, j and k are 3 and 1, then I get plus 1. So, j is 3, that means I have A 3, k is 1, B 1. Okay. The other combination when I is 2 is when j and k are 1 and 3. In that case, epsilon is equal to minus 1. Okay. So, I get minus A 1 B 3. Similarly, you can do it for I is equal to 3, in which case you will get E 3 vector into, you can do it quite easily. The first is when I is 1 and j is equal to 2, in that case epsilon is equal to plus 1. Okay. So, you will get A 1 B 2, and the other cases where I is 2 and j is 1, and you will get minus 1 there. Okay. Okay. So, applying this particular formula, we see that the result that we get for the cross product is identical to what we had in this case. Okay. So, this also gives me the result for the cross product. Okay. So, in this case I have one unit vector and I have two dot products, because there are these two indices which are repeated, j is repeated and k is repeated. Okay. So, the cross product itself can be considered as the dot product of this epsilon I j k, which is actually a third order tensor. It has 3 indices with 2 vectors. Okay. So, the cross product, once you get used to second order, third order tensors, the cross product is no different from a dot product. Okay. Now, let us make a notational simplification. Okay. Yeah. So, in this case I had written down u vector as u I times E I. There was one index I that was not repeated, and that index was summed over 1 to 3, and there was a unit vector next to it. Similarly, for A and B, for the dot product, now there is one index, but that appears 2 times, A I B I. It appears 2 times, I appears 2 times, and there is one summation. Okay. For the second order tensor, on the other hand, that I wrote down for you, there are summations over 2 indices T I j. Each one of those appears 1 time. There is a summation and a unit vector. Without loss of generality, okay, without any notational ambiguity, one can remove the summations and the unit vectors. Okay. The unit vector as well as the summation can in general be removed. Okay. This unit vector, the summation. Okay. And so, I can just write this vector, this I can write it as just u I. Okay. There is one index which is not repeated. That means that when the index is not repeated, there is a summation and there is a unit vector. That index represents the one fundamental direction, in this case the direction of the velocity field itself. Okay. Similarly, in this case A I, this is B I. Okay. This dot product I can write it as A I times B I. One index I, that means there is a summation, but that index is repeated 2 times, that means there is a dot product, it is summed over. Okay. So, there is a dot product. Okay. In my notation, the stress tensor, I will just write it as Tij. It has two indices which are not repeated. That means, there are two unit vectors and two summations, just as I have here. There are two unit vectors just as I have here. Okay. So, the index is not repeated. Whenever there is an index that is not repeated, that means there is a unit vector associated with it and a summation. That means that the order of the tensor is equal to the number of unrepeated indices that are present, okay, in this tensor. How about this? Okay, so, I have here a I b j times delta I j with two summations. You can see that I is repeated 2 times. That means, there is a summation, but no unit vector. It is a dot product. J is repeated 2 times. That means, there is a summation, but no unit vector. So, there is a dot product. So, both of these A and B vector are dotted separately with delta. Delta I j has 2 indices, though it is a second order tensor. Okay. So, delta I j, if I expand it out, will be delta, okay, delta I j E I E j. Okay. So, in my shorthand notation, I just wrote this as delta I j, whereas in my longhand, I have delta I j with 2 unit vectors sitting next to it. Okay. So, this second order tensor is dotted with both the vectors a and b to get the dot product of the two vectors, which is a I times b I. And what I have here is once again one repeated index and one summation, no unit vectors, because it is a scalar. This thing is what is also called as the identity tensor. Okay. In longhand notation, if I write it down, it will be delta 1 1 E 1 E 1 plus delta 1 2 E 1 E 2 plus etc. However, delta is 1 1 is 1, delta 1 2 is 0, delta 1 3 is 0, and so on. So, if you expand this out in a matrix form, if you write it, you will just get an identity matrix. Okay. That is why it is called the identity tensor. Okay. Written in matrix form, it is the identity matrix, and this tensor is actually independent of coordinate systems, okay, just as the antisymmetric tensor is. So, back to my cross products. Okay. If I were to write this in my indicial notation, okay, I would just write A cross B is equal to epsilon I j k A j B k. Okay. So, this, if you look at the right hand side, there are 3 indices I, j and k. Only one of these is not repeated, okay, that is I. Okay. So, that gives you one direction, one unit normal and a summation over I. J is repeated 2 times, implies a dot product. K is repeated 2 times, it also implies a dot product. So, there are no unit vectors, there are 3 summations and 1 unit vector corresponding to I. So, it is a vector, okay, what you get in the end is a vector. Okay. So, the cross product is no different from a dot product. Okay. We can reduce it to a dot product by dotting this antisymmetric tensor with the 2 vectors that we are considering. Okay. Now, one has to be careful when using cross products, because the result could depend upon the coordinate system that you are using. Okay. So, let me just try to explain that. I have 3 unit vectors. Okay. So, you know that E 1 cross E 2 is equal to E 3. Okay. If I take the cross product of 2 vectors E 1 and E 2, it is perpendicular. Okay. As per the right hand rule, it has to be in the plus E 3 direction. Okay. So, this is for a right handed coordinate system. Okay. but there is no reason why we should use only a right handed coordinate system. One could as well do the analysis in a coordinate system that is left handed. Okay. So, if I chose a left handed coordinate system, okay, then my unit vectors would be E1, E2 and E3. It's a little long. In this case as well, we know that E1 cross E2 is equal to E3. Okay. So, it appears that if I have two vectors E1 and E2, the cross product of those two is upward in a right handed coordinate system and downward in a left handed coordinate system. Okay. It seems like a trick question, but it is not. Okay. In fact, in a right handed coordinate system, the cross product that you get is opposite to what you get in a left handed coordinate system. The cross product depends upon the convention that you use for calculating that cross product. Okay. If you go back to fundamental mechanics courses, you know that the torque is defined often as x cross f. So, if you have some object and you have a force exerted on that object at a certain distance from the center of mass, the torque vector is often written as the cross product of these two. Okay. In a right handed coordinate system, the torque will be one way. In a left handed coordinate system, it will be the opposite way. That is consistent. There is no inconsistency there. Okay. The reason is because the torque is a derived quantity. X and f are measurable quantities. Okay. For example, the distance can actually be measured. Okay. The distance is the vector pointing from the initial to the final location. That displacement is actually a measurable quantity. The force is a measurable quantity. Basically, the force is equal to the mass times acceleration. The acceleration is the rate of change of velocity. So, that is a vector, that is a real vector. The position is a real vector. Okay. If you take the cross product of these two, the result depends upon coordinate system. It points in one direction for one coordinate system and in the opposite direction for the other coordinate system. Okay. So, because of that, the torque is not a real quantity. It is often what is called as a pseudo vector. For a given configuration, you can measure distance, you can measure force, but the direction of torque depends upon the coordinate system that you use. Okay. So, if you have one cross product, okay, so this is basically equal to epsilon I j k x j f k. If you have one cross product, then you get a pseudo vector. Okay. Because the sign of this epsilon, okay, the direction in which this epsilon vector points depends upon the coordinate system that is being used. Okay. So, one has to keep this in mind when interpreting results. If you take the cross product of two real vectors, as in this case x and f, you will get a pseudo vector, okay, whose direction will change if you go from a right handed to a left handed coordinate system. Okay. On the other hand, the linear velocity, for example, is written as r cross omega. Okay. The linear velocity is often written as v is equal to, okay, the displacement crossed with the angular velocity. Okay. In this case, the linear velocity is a real quantity, displacement is a real quantity. So, both of these remain the same when you interchange from right handed to a left handed coordinate system. That means that this angular velocity has to be a pseudo vector whose direction will change depending upon whether you use a right handed or a left handed coordinate system. Okay. So, that is something that has to be kept in mind. When you take a cross product, you should if there is one cross product between real quantities, you get a pseudo quantity whose direction changes depending upon the right or left handed coordinate system used. On the other hand, if you have a cross product involving one real and one pseudo vector, well, you will end up with a real vector, because omega changes in sign, that cross, that epsilon also changes direction. Therefore, the velocity will be independent of the coordinate system used. So, this cross product makes a distinction between two different types of quantities, the real quantity and the pseudo quantity. Okay. Okay. So, let us briefly review what we done so far in vectors and tensors. Okay. The velocity u vector is just written as ui. Okay. Implicit in this notation is that there is a unit vector there and there is a summation there. Whenever one has a doubt about this, we go from the shorthand notation ui to the complete longhand, including all the other ei as well as summation. Okay. Second order tensor is written as Tij. Okay. Implicit that there is one two summations for each of the unrepeated indices and two unit vectors. Okay. The dot product is equal to ai bj. Okay. These are two vectors and the dot product has the identity second order tensor in it, okay, ai bj delta ij. In this case, there are two indices I and j which are repeated 2 times each. That means, there is only 2 summations and there are no unit vectors. Okay, there are no unit vectors because each index is repeated 2 times. Okay. The cross product is written as epsilon I j k a j b k. Okay. Note that when I interchange any two indices, epsilon gets reversed in sign. Okay. So, when I interchange any two indices, I can write this as epsilon I k j. Okay. Because I interchange j and k, I get minus sign. Okay. And this is equal to minus b cross a, okay, because whenever I take the cross product, I take the one that the index that appears the second here. I is the first index, that is the free index, gives you the direction of the resulting cross product vector. Okay. So, I is the first index which gives you the direction of the vector. J is the second index and k is the third index, and epsilon I j k a j times b k is equal to a cross b. Therefore, epsilon I k j, that means that I have to take the second index b crossed with a. Okay. And because the tensor is antisymmetric, I get the familiar result that a cross b is equal to minus b cross a. Okay. The rules to be followed. Represents some fundamental direction. Okay. And for this, there is summation plus unit vector. Okay. Okay. Make it clear. If an index is repeated 2 times within the same expression, that means there is a dot product, and with this there is only a summation. With this there is only a summation, there is no unit vector because the dot product is a scalar. Okay. And just for consistency, index repeated 3 times. Index repeated 3 times is means there is some mistake, because once it has been repeated 2 times, it has already been summed over, it has already become a scalar. You cannot have that same index repeated a third time. Okay. So, With these brief rules, we can go ahead and work with vectors, tensors of any order without having to worry about the distinction between dot products, cross products and tensors of different orders. Okay. For example, I said that the tensor Tij was equal to summation I is equal to 1 to 3 summation j is equal to 1 to 3 of Tij Ei dotted with Ej. Okay. What is Tii? In this case, there is one index that is repeated within the same tensor 2 times. There is one index that is repeated within the same tensor 2 times. So, therefore, if I expand this out, what I am going to get is, for this particular index, I am going to have one summation and no unit vectors, because there are no unrepeated indices. Okay, summation I is equal to 1 to 3. Okay, there are no unrepeated indices, so there is no unit vector. This is a scalar, one summation. So, this is equal to T11 plus T22 plus T33. Okay. So, for those of you that know recall your matrices, this is the trace of that stress tensor matrix. Okay. So, for example, I had written the stress tensor as in this matrix form. T11 plus T22 plus T33 is the sum of the diagonal elements. It is also called the trace of this matrix. Okay. When I take products, I do not have to take the cross product or dot product alone. Okay. I could, for example, define a product as A B, okay, without any dot or cross sitting inside. Okay. So, this, if I just take this product A I B j E I E j with 2 summations. With 2 summations A I B j E I E j. In my shorthand notation, I do not write down the summations and the unit vectors. So, this just becomes equal to A I B j. This has 2 unrepeated indices, therefore, it has 2 fundamental directions. There are 2 unit vectors, 2 summations. That means that this product is a second order tensor. Okay. It is called the dyadic product often. It is often called the dyadic product of 2 vectors. So, I do not have to take just the dot or cross product. Dot product will give me a scalar, cross product will give me a vector. A dyadic product will give me a second order tensor in this case. Okay. So, I can take the dyadic product of 2 vectors to get a second order tensor. Similarly, you can take the product of anything. Okay. So, for example, you can write down A I S j k. Okay. This basically is the direct product of one vector with a second order tensor. This obviously gives me a third order tensor. Write it out in long notation, summation I is equal to 1 to 3 A I S j k E I E j E k. It has 3 unit vectors, therefore, it is a third order tensor, the dyadic product, okay, where A and S are a first and a second order tensor respectively. Okay. I could also define another one A I S I k. Okay. In this case, now there are 2 indices. So, there are 2 summations, there are 2 indices I and k, summation I is equal to 1 to 3, summation k is equal to 1 to 3 of A I S I k, and there is only one unit vector left, because there is only one unrepeated index, and that is E k. So, this is a dot product between a first order vector, a first order tensor, and a second order tensor. The result is first order, because one dot product reduces the order by 2, because you are dotting 2 directions. So, it reduces it by 2. So, whereas I have a first order vector and a second order tensor, when I take the dot product, I get a vector. Okay. and similarly these can be done for tensors of all orders. And the other important thing to remember is that I told you these rules to keep in mind. These are for just for the vectors and tensors themselves. Okay. I can also write equations equating different vectors and tensors, okay. And one has to remember that the fourth rule, okay, which I had not put up there, was that in equations the order and unrepeated indices of all terms are the same. The order of all terms have to be the same. For example, I cannot equate a vector to a third order tensor. The vector has 3 components, the third order tensor has 3 times 3 times 3, that is 27. So, I cannot equate a vector to a second order tensor, I cannot equate a vector to a scalar, okay, it makes no sense. All terms when you write an equation have to have scalars, vectors, tensors of the same order. The other thing is that all the unrepeated indices have to be the same, because each unrepeated index represents one particular direction and the equation is some kind of a balance for that particular direction. So, all the unrepeated indices on all sides of the equation have to be the same. Okay. So, for example, I can write an equation of the form a I b k k plus s l m h l m I, okay, is equal to C I. This is a valid equation because each of these terms is a vector. The first term a I times b k k, k is repeated, so it is a scalar. So, there is only one vector. Second term s l m times h l m I, L and m are repeated. So, once again one gets a vector, and on the right hand side also there is a vector. So, the unrepeated indices as well as the order of each term in the equation have to be exactly the same when you write an equation. Okay. And the other rule to remember is that all terms have same parity when going from right to left handed coordinate system. Okay. That is, if one term changes sign when you go from right to left, all other terms also have to change sign. If one term remains unchanged, then all the terms have to remain unchanged. Otherwise, what will happen is that if the equation is valid under right handed coordinate system, when you go to left handed coordinate system, some terms have changed sign, some have not, and the equation is no longer valid. Okay. So, a valid equation can be written only if all terms have the same parity under going from right to left handed coordinate system. That is, all terms either have to be pseudo vectors or tensors, or they have to be real vectors or tensors. Either all have to change sign or none has to change sign. So, with this brief background on vectors and tensors, mostly what we did was notational simplifications along with simpler ways of writing things like dot and cross products. As we will see, these simplifications will have a significant consequences when we write down equations later on. So, after having done basic vectors and tensors in this lecture, in the next lecture I will do vector calculus. How do you translate differentiation and integration when you are working with vectors in 3-dimensional space? Okay. So, we will continue that in the next lecture. Please go through this again before you come to the next lecture, so that you are clear about the fundamentals here, and we will continue in the next class. So, we will see you then.